anything from today, you can, or if you want to use your own piece of paper, whatever you want to do. So we did kinetics in class today, so this kind of works out because now we're just going to be able to kind of review all of the important aspects of kinetics. So this is big idea 4, which means we only have 2 more big ideas, and then we have the science practices, which is like the lab-based stuff. If you remember the factors that affect reaction rate, we have the state of reactants. So the rate of reaction actually increases as we go from solid to gas, because the more collisions you have, the more or the faster your rate will be. So since gases move around faster and have more collisions, your rate of reaction is actually the fastest when you're dealing with gases, and it's the slowest when you're dealing with solids. The rate of reaction increases as we go from solid to liquid to gas, and then the greater the surface area you have, the faster the rate. So, like the example that I always use is sugar crystals dissolve faster than a sugar cube. And that's because, think about surface area as exposure. The more exposure it has, the faster it reacts. So since the crystals have like exposure on every side, where the sugar cube just has the sides of the cube, the crystals will dissolve faster. Temperature, again, refer back to collisions. So always reference collisions when you're thinking about rate of reaction. And so the more kinetic energy, remember, temperature equals kinetic energy. So if you're asked a question about kinetic energy, look at the temperature. And then concentration, the more reactants you have, the more concentrated, the faster it reacts. And then when you have a catalyst, when you use a catalyst, it lowers the activation energy, which makes your rate faster. And so this is all based on the collision theory, which says that reactants have to collide with correct orientation and with enough energy. So you need right orientation, and you need to overcome the activation energy. So this was part of last year's free response question, and yesterday we looked at part A. But we're just going to focus on part C down at the bottom. So you have all this information about sodium bicarbonate reacting with acetic acid, but it says the student observes that the bubbling is rapid at the beginning of the reaction, because we're forming a gas, and then gradually slows as the reaction continues. Explain this change in the reaction rate in terms of collisions between reactant particles. So when you're explaining part C, you have to talk about the reaction rate and collisions. So as you're seeing fewer and fewer bubbles, what's happening to the reaction rate? It's getting slower, right? It's slowing down. You're not seeing as many bubbles. And so what does that mean in terms of collisions if your rate is slowing down? You have less collisions. So the scoring guidelines for this, it just talks about, because both reactants are being used up, you're going to have fewer collisions because the concentration is decreasing. So since you're having fewer collisions, the reaction rate slows down. Okay, so determining the order of reactants. So if you remember, you have to determine it experimentally. And so you always look at the data that they give you, and you focus on when one changes but the other stays constant. You look at what happens to the rate. So when A is doubled, rate doesn't change. That means it's 0 order. If one doubles and the other doubles, that's first order. If one doubles and the rate quadruples, right, that's second order, because 2 squared is 4. And so then you always write your rate law only based on reactants. So you only include reactants in the rate law, and you always have rate equals K times whatever the concentrations are. This little bullet point right here is really, really important. So lowercase k is your rate constant, and that's solved by plugging numbers into the rate law. Don't forget to give units as you work through. Now, your units for k can change. So when you're looking at units for k, just plug in everything here. Remember, moles per liter is molarity. So this is molarity per seconds. Here's molarity. So when you're solving for k, just plug your units in and cancel everything out to see what you have left. And then when you are looking at the order of reaction with reference to time, you can look at the graphs. So if it's 0 order, your concentration versus time is straight. If it's ln, versus time, and that gives you a straight line, then it's first order. And if you're 1 over concentration versus time gives you a straight line, it's second order. And then the first and second order integrated rate laws can be found in the kinetics section of the equation sheet, and that's looking at like your ln of concentration versus time, and your 1 over concentration versus time. So the integrated rate law lets you solve for concentration at a given time. And so really the difference between the rate laws, so like this differential rate law up here, which is rate equals k times the concentration of B, that lets you look at rate versus concentration. The integrated rate law lets you look at concentration versus time. So it all is just dependent on what you want to find. Always remember, and we kind of hit this in class, when you are given graphs, you use the graphs to figure out what the order of reaction is, but you always use the concentration versus time to look at initial information about the reaction. So if you need initial concentration, always use this concentration versus time to give you, initial concentrations or half-life or anything like that. The ln and the 1 over, that just helps you figure out if it's first order or if it's second order. And then this free response question is the one that we did in class today. This is from last year's test, and so if you remember, you had these 3 graphs, and one of the questions said, use the data plotted in the graphs to figure out the order of reaction. And so you just had to look and see which one was the straight line, and since the 1 over concentration versus time gave us a straight line at the second order. And then part C said the initial rate of reaction was 0.001. Calculate the rate constant at 625 Kelvin. And so since it says that the initial rate of trial 1, if you look up here, there are 2 trials. When you are looking for initial amounts, always use concentration versus time. And so if we want trial 1, here is our initial concentration in trial 1. It's 0.02. If you know your initial concentration and you know your initial rate, you can find the rate constant. And this second explanation was weird and confusing. You just look at this one up here. So you can plug everything in and you can actually find your rate constant. So then looking at half-life, half-life is just the time that's needed for your concentration of your reactant to reach half of its initial value. So if you start with 100 moles of something, your half-life is the amount of time it takes to get to 50 moles. And then the time it takes to get to 25, and then 12.5, and so on. Half-life remains constant in a first-order reaction. And that was looking at, I think it was the question from the 2014 test in class today. It said, how do you know it's a first-order reaction? Well, if you're at the same temperature, no matter what concentration you're looking at, your half-life should remain constant. And so that kind of helps you with the first order. And that's because half-life does not depend on concentration in a first-order reaction. And we only deal with half-life in the first order because it's the one that doesn't depend on concentration. And so this T1 half equals ln2 over k. ln2 is the 0.693. That's where that number comes from on the equation sheet. But this is on the equation sheet, this T1 half. And so if you know half-life, you can find k. If you know k, you can find half-life. And so this just shows a particle diagram of looking at half-life. So you start with 12 molecules, then after whatever your half-life is, you get to 6 molecules, so it looks like your half-life is 30 seconds. And then after another 30 seconds, you cut that down by a half. Okay, so then collision theory. So your collision theory is just going back to everything has to collide with the right orientation and enough energy. So you need enough energy to overcome activation. You need the proper orientation. So they have to hit, maybe it's NO combining with HF. Well, maybe it's your O and your H that have to collide. And if your O and your F hit, then that's not going to be a correct collision. That's not going to be the proper orientation, and so the reaction might not take place. In any reaction mechanism, the rate law, so an elementary step. So in this case down here, you have a 3-step mechanism. Each one of these steps is an elementary step. To write the rate law of an elementary step, you just look at the stoichiometry. And then remember that to find the rate law of the overall mechanism, you just look at the rate determining step. You look at the slow step. And so looking at this down here, we have 3 steps, right? Step 1, 2, and 3. Step 1 is our slow step. That is good. It's good if your first step is your slow step. It's less algebra. And so to write the rate law for your slow step, remember it's always rate equals K times whatever. So because this is my slow step, rate equals K times the concentration of N2O5. That's my rate law. It doesn't match my overall reaction, but that's fine because it's a reaction mechanism. When you're looking at the value of K, so the larger your value of K, that actually means you have more molecules colliding and reacting. So the larger value of K would actually tell us that we have more collisions happening and a faster rate of reaction. So if maybe you're given 2 or 3 values of K, the one that's bigger is actually the one that has a faster rate because you have more molecules reacting. Okay, and so again, to write the rate law of a reaction mechanism, you just do rate equals K times your reactant. Products are never included in a rate law. Okay, so then looking at different collisions, and this graph shows what's called the Boltzmann distribution, and really what it shows us is how many molecules have a specific speed. So if you look at A here, that's this blue peak. What this is showing us is that a majority of our molecules have a speed, somewhere in here, so somewhere from 0 to 500. Peak B is showing us, if I just look right here, most of our molecules have a speed probably between like 250 and 750. And then C, we could say, somewhere maybe 400 to, 1500. And then D shows that most of our molecules are, 500 to, 1750. And so all this shows us is the further spread out your peak is, the more speed your molecules have. So in this case of this question, it says, which curve indicates the particles most likely to produce collisions that result in a chemical change? So in order to produce, or in order to have collisions, we need lots of speed, right? They need to be colliding frequently. And so we want to pick the one of these peaks that has most of its molecules moving fastest. So which of these peaks has molecules moving the fastest? And that's going to be peak D. Because if you notice, peak D comes all the way over here. So you even have some molecules moving at like 2,500 meters per second. But D has more molecules moving faster. A has most of its molecules right in this range. We want them to be moving the fastest. And so the more spread out this peak is, that means the more molecules that are moving fast. And then the more likely to have collisions and have a fast reaction. So then temperature and reaction rate. So this shows us 2 energy diagrams. So this one, our reactants have low energy, our products have more energy. And then in this reaction B, here's my reactants, my products actually have less energy. And so this is in order for both reaction A and reaction B to proceed in the forward direction at the same rate, which reaction would need to be at the higher temperature and justify your choice. So what we want to look at is which of these has the higher activation energy? Which one takes the most amount of energy to actually work? A, right? A has a large activation energy. You have to put in a lot of energy in order for that reaction to even work. And so the higher the activation energy, the higher the temperature you want the reaction to run at. Because when you put a reaction at a higher temperature, that's making all the molecules move really quickly, and then they're going to be more able to overcome the activation energy. So for this question, Since reaction A has a greater activation energy, it's going to normally be slower, but if we want them to be at the same rate, then we just need to put reaction A at a higher temperature. And then remember, reaction A here shows the products having more energy, which means your reactants have to absorb energy. So reaction A is showing an endothermic reaction, and reaction B is showing an exothermic reaction. And then looking at reaction mechanisms. So reaction mechanisms are just multi-step. And so this example says a reaction and its rate law are represented above. So here's the overall reaction, and here's the rate law. A chemist proposes two different possible mechanisms, which are given below. Based on this information, which of the mechanisms are consistent with the rate law? So when you're given a reaction mechanism, which part of the mechanism determines the rate law? Slow step. So this first mechanism, the first step is the slow step. So how would I write the rate law for this slow step? Rate equals what? So K times, concentration of X2. It's always, your rate law is always based on your slow step, and then the stoichiometry, and since there's no coefficient, it's assumed to be 1. So mechanism 1, the rate law would be rate equals K times the concentration of X2. Does that match this rate law given up here? Yes. Okay, let's look at mechanism 2. How would I write the rate law for mechanism 2? All right, same thing. Based on the slow step, rate equals K times concentration of X2. So both of these mechanisms match this overall rate law. Now this also says list the intermediates in each mechanism. So what are your intermediates? Like what is an intermediate? Yep, something that's made and then that's used up. So if we look at mechanism 1, what is an intermediate? Okay, XY2, because that's made and then used up. Anything else? X, because you have 2X here, you have 1 here and 1 here. So X and XY2 are intermediates in mechanism 1. And then we also have the X here. And then what else is an intermediate? Okay, X2Y, Y, then we have one more, XY. All right, so if it's made and then used up, it's an intermediate. And also notice your intermediates are not in your overall equation. And so make sure that your mechanism, when you add all 3 steps up, it should equal this overall reaction, kind of like Hess's law. Okay, so then looking at this one, so now we get into the algebra. So the rate law for a reaction is found to be rate equals K times A squared times B. So then it says what's the intermediate and which of the following mechanisms gives this rate law. So looking at all 3 of these, what is an intermediate? Okay, E, because it's produced and then it's used up in all 3 of them. Okay, so now this says which of the following mechanisms gives this rate law. So we have to work through some algebra. Your rate law is based on what step of your mechanism? The slow step. So if we look at mechanism 1, we have, so if we look at mechanism 1, my slow step, here we go. Okay, so mechanism 1. What is happening? Un momento, por favor. Let me write on you. Alright, so mechanism 1. Let's write our rate law. Rate equals what? So here's our rate law. It's always based on the slow step. So for mechanism 1, our rate law is rate equals K times the concentration of E times the concentration of B. because it's based on our slow step. But what is E? An intermediate, and you cannot have an intermediate in your rate law. And so what we have to do is we have to go back and use the fast step, which is at equilibrium, to solve for E and plug everything back in. So if you remember, equilibrium, and we're going to talk more about equilibrium next week in class and after school, but equilibrium is when the rate of your forward reaction is equal to the rate of your reverse reaction. So the rate of your forward reaction equals the rate of your reverse reaction. Now when you write the rate of your forward reaction, you take the reactants, rate equals K times concentration of your reactants, and you can set it equal to the rate of your reverse, so whatever the reactants would be if you're going the other way. And so what I did here is I just wrote my rate law for both of them. Now you could write like Kf, so you could have Kf times the concentration of A times the concentration of B, because those are the reactants for the forward, equals K times the concentration of E, because that's the reactant if you're going in the reverse. Now I'm going to rearrange this to solve for my intermediate. And what's my intermediate here? E. So I'm going to solve this. So Kf over Kr times A times B. Now K is K. Don't get caught up in all your K's. You could really cancel them out and not worry about it, because when you have a K, it's a K. Okay. So let's plug E back in for our rate law of our slow step. And we get rate equals K, right, just your rate constant. E is actually A times B, and then don't forget to multiply by B again. So if we do B times B, what is that? B squared. So my rate law for mechanism 1 is K times A times B squared. Does that match what we were given up here? No. So mechanism 1 does not work. I'm going to skip 2 for a second. I'm going to come down to 3. 3 is nice because our slow step is our first step. How would I write the rate law for mechanism 3? K times A squared. No intermediates in it, so we're good. Does that match the rate law that we were given? No. Now, if you went through the algebra, like in mechanism 1 for mechanism 2, it's actually similar because the fast step is the same. What you're plugging E in for is different. Because what's your rate law for your slow step in mechanism 2? Yeah, E times A. So we can actually plug in what we solved for E in mechanism 1 down, and then you get K times A squared times B. And so mechanism 2 is actually the one that matches this rate law. So that's all the algebra. I know we didn't go through the algebra in class, but now we did. Okay, and so then again, E is the intermediate, and then only mechanism 2 is consistent. So then looking at reaction mechanisms and going along with the energy profiles, so this is just looking at your reaction diagrams. This is draw and label the axes for the profiles and then match the curves with the appropriate description. So when you label the axes for each one, and I'm going to put them all up here because they're the same every time. Your axis, your y-axis is always energy. Your x-axis is always reaction, right? Reaction pathway, just reaction, but it's just kind of what's happening during the reaction. So then it says to match the curves with the description. So if we look at A, it says it's an exothermic reaction with a two-step mechanism where the first step is slow. So when we're looking at these reaction mechanisms, how can we determine which step is the slow step and which one is the fast step? So like, let's see. Right, the one with the more activation energy. So let's try to find, well here, let's go through this way. If it's a two-step mechanism, what should we look for in the diagram? 2 peaks. Okay, so we have 1, 2, 3, 4. Okay, so those 4. If it's exothermic, what should we look for?
Second line would be lower.
Right, second line would be lower. So that brings us to the top middle one and the bottom right one. So then which, between the top middle and the bottom right, which one has the first step having a higher activation energy? Bottom right. Right, so the bottom right one goes with A. So B says endothermic reaction with a 2-step mechanism where second step is slow. Okay, so now we want 2 steps, so we want 2 peaks. We want endothermic now, so your product should be higher. And we want second step to be slow. Which one would that be? Bottom middle. Okay, then C, exothermic reaction with 2-step mechanism where second step is slow. Okay, top middle. And then endothermic reaction, well, that's going to be the only other 2-step one left. And then E is an exothermic reaction with 1-step mechanism. So if it's exothermic, your product should be lower in energy. And then if it's endothermic, your product should be higher in energy. So that's just looking at your reaction diagrams and looking at if it's a slow step, it needs a higher activation energy. Right? If it's fast, it's going to have a low activation energy. If it's slow, it's going to need a high activation energy. All right, so last part of this is actually just looking at catalysts.
Wait, this is the last part?
Yeah, I know. So catalyst, the whole point of a catalyst is to lower the activation energy. And so you can see up here you have just the activation energy lowering, and that's why reactions go faster. So a catalyst can actually help form a new intermediate by stabilizing the activated complex or the transition state. One example is the Haber process, and so what it does is it lowers the activation energy by using a catalyst, and then it lets the reaction happen more quickly. And then, very last slide, so catalysts, again, provide alternative mechanisms to lower the activation energy, and there are different types of catalysis. So there's acid-base. That's just like if you think about acids and bases, right? A proton is transferred. So in acid-base catalysis, a reactant will either gain a proton or lose a proton, and that changes the rate of reaction. In surface catalysis, you actually have something being formed on the surface of something, like platinum maybe, and that's when you can form a new intermediate. And so because you're forming a new lower energy intermediate, it makes the reaction go faster. And then in enzyme catalysis, that's more with biology. You have your enzymes that actually bind to reactants to lower the activation energy and create new intermediates. And so you can see here with a catalyzed reaction, it lowers the activation energy. Even though this would produce a mechanism, because it'd be 2 steps, it still has lower activation energy, and so it would actually go more quickly.